All right, let's look at the 1.3 set. We're looking at tables. We're going to decide if it's linear, quadratic, or neither, or exponential, I guess is the other one we're used to. It's asking us to write the recursive, but as a bonus, we're going to also see if you can write the explicit. So let's take a peek. Going from a -6 up to a -4, up to a -2, up to 2. Do you see that this is increasing by 2 with every jump? Okay, when we see that first difference is constant, we know that it's linear. Of +2. So to write the recursive, we go. Now, remember, we can use any term in this table, okay? But I'm going to keep using this top one. But if you'd like to use the 0, 0 or the 1, 2, because it makes it a little bit easier to write, feel free. So using this, -3, -6, we're going to go f of -3 equals -6, f of x equals f of x minus 1. And then we're adding 2 each time to the previous term. For that explicit, for this linear, we're going to say f of x equals, begins with -6, adding 2 each time to the x minus a -3. Now let's write this out so you can see. X minus a -3 turns into x plus 3. How'd you do? On that explicit. Okay, let's look at the next table. Next table goes from a 4 down to a 0. I'm sorry. So this one's subtracting, right, from 4 down to 0. So it's down 4. Then from 0 down 2. Then it stays the same. From a -2 to a -2, there's no change. Then it goes back up 2, back up 4, and up 6. Okay, this is interesting. We notice that there is no constant first difference, so it's not linear. Well, let's check out the second difference. From a -4 to a -2, that would be adding 2. From -2 to 0, oh hey, check this out. So we would say this is quadratic because there is a constant second difference. Now, if you're worried about these additions and subtractions that I just got right here, remember to grab a calculator and do it on a calculator so that you're not stressing yourself out about the negatives. So our pattern is quadratic because of the constant second difference. Now let's go write the recursive. Again, using any term, but I'm going to do the top term. F of -3 equals 4. F of x equals f of x minus 1. Now, how do I get that linear change? Pick any row. Let's start with that row. Begins with 0, adding 2 each time to the x minus times 0. It's like we ignore this. We start here adding 2, x minus 0. So simplifying this down gives me 2x minus 0, 0. It's just 2x. Let's go check out any other row. I'm going to do this row next. Again, doesn't matter which one. So this is this row. Begins with 6, so we ignore that guy right there. Begins with 6, adding 2 each time to the x minus time 3. Let's simplify this down. 2x minus 6. 6 minus 6. Do you see that zeroes out again? Leaving me again with the 2x. So we know that this 2x is correct as the linear rate of change for my recursive. Okay, now for the explicit. Remember, this is a bonus. It didn't ask us for the explicit. Let's see what color I want to do. I'll just do it in black. F of x equals, remember that all quadratics start with an x squared. Starting with this 0 term, if I plug in 0, I should get a -2. So let's just try straight up, plug in 0, get a -2. That's coming from this part right here of where I plug in 0, my input. It should give me output of -2. Let's go test a different one and see if it works. F of 1 equals 1 squared minus 2. So 1 squared is 1 times 1. 1 minus 2 is -1. Notice that if I plug in 1, I'm supposed to get a 0. So shoot, it doesn't work. Just doing an x squared minus 2 wasn't enough. So should there be some sort of another x in there or something like we saw on the pattern before? So plugging in 1 squared minus 2 times 1. So in this case, it gives me 1 minus 2 again, which is negative this. Nope, not enough. Let's try something else. Let's just try x. 1 minus 1. Okay, well that would give me 0. Let's go test it out for a different pair. Let's go f of 2 is equal to 2 squared minus 2. So that's going to give me 4 minus 2, which is 2. Plugging in a 2, I should get a 4. It doesn't work. Do you see why they didn't ask us for the explicits on this one? And why it's a bonus? I want you guys to try plugging in different scenarios as a bonus to see if you can come up with explicits on these. And we're going to go over them in class. Now, for sure, I know it is an x squared. Why? Because of that hint where if the constant difference of 2, half of that constant difference is 1. So it for sure is a 1x squared. You're just trying to figure out what comes after that, if anything, okay? So keep that in mind. I want you to try as a bonus to get some of these explicits, but that's why the explicits are not required. They're just asking for the recursives at this time, okay? And I'll go over the explicits in class. Okay, jumping to this guy, we're noticing from a -5 up to a -10, it added 5, added 5. It's also adding 5 again. This one's so pretty. It's got a constant first difference. The pattern is linear because it has a constant first difference. And the recursive goes f of -3 equals -15, f of x minus 1, plusing 5. I asked you to try the explicit as a bonus, not required. F of x begins with -15 adding 5 each time to the x minus a -3. Turns into an x plus 3. Remember, you can use other terms here if you like. Next one is going down to. That means pattern is also linear because of that constant first difference of subtracting 2. The recursive, f of -3 equals 24, f of x equals f of x minus 1 minus 2. Explicit as a bonus begins with positive 24, subtracting 2 each time to the x minus a -3. Remember that the explicits are bonus. Okay, this one is going from a 48 down to a 22. I'm going to actually pull out my calculator here. Where did I put it? Let's see what this one's going down by. So 48 minus 22 would be down 26 minus 6 is down 20, down 6, then up 4, up 14, and what's 42 minus 18? Up 24. Sorry guys, could you see the error I made? 22 minus is 16, hang on. Okay, what did I do? 22 minus 48. This is down 26. And then 6 minus 22 is down 16. And then it's down 6, and then it's up 4, and then it's up 14, and then it's up 24. So I don't have a linear here because there's no constant first difference. So let's look at the next jump. Next jump goes from negative 26 up to negative 16. Do you see the jump up of 10? From negative 16 to negative 6, do you see the jump up of 10? From negative 6 up to 4, from 4 to 14, from 14 to 24. I do have a constant second difference. Writing the recursive, f of negative 3 equals 48, f of x equals f of x minus 1. How do I get that linear rate of change? Pause the video, make sure you go over and try it. Pick a row, any row. No, let's not do that one. Let's do the 0 row. Oops. Okay, this one would say begins with negative 6 adding 10 each time to the x minus times 0. And that's just going to leave me 10x minus 6. How'd you do? Now, let's say, do I think I made an error on this? Let's always test out another row if you want to be safe. Keep doing that, sorry. Let's go this row, for example. Begins with 14, adding 10 each time to the x minus time 2. 10x minus 20, 14 minus 20 is going to give me minus 6. Okay, I just got the same thing as I got over there. I am good to go. So picking any row to find that linear rate of change for your recursive. Again, as bonus, try for the explicit. We'll go over it in class. Okay, next. From a 4 to a 1 is down 3. From a 1 to a 0 is down 1, and then up 1, up 3, up 5, up 7. Okay, not linear, no constant, first difference. Notice though that this is going up 2. And so yet again we have our quadratic. F of negative 3 equals 4. F of x equals f of x minus 1 plus that linear rate of change. Go off to the side, pause the video, try it. Pick any row. Let's see how you did. Begins with 1, adding 2 each time x minus times 0. How'd you do? And by the way, you can put this as parentheses or put it without parentheses. Both are correct. Try that explicit as bonus. Okay. I want you to skip this one because we're going to do this one tomorrow in class. And then hopefully you are ready to go. That's it.